Mathematical Foundation of Deep Neural Networks, DNN, Nodes. Each node in a deep neural network, DNN, follows a mathematical function that processes inputs and produces an output. These computations are based on linear algebra, calculus, and probability theory. Let's break it down mathematically. Pradeep K. Suri, author, researcher, and AI/ML architect. One mathematical formula for each node. Each node in a DNN performs the following operation. Z equals sigma I equals 1 yxi plus b z equals \sum underscore I equals 1 caret n w underscore I x underscore I plus b z equals I equals 1 sigma yxi plus b a equals f, z, a equals f, z, a equals f, z. Where 19 underscore xi equals input from previous layer. W underscore iwi equals weight assigned to each input. BBB equals bias term. ZZZ equals weighted sum, linear transformation. F, Z, F, Z, F, Z, equals activation function applied to the output. AAA equals final output from the node. Two activation functions, nonlinearity in nodes. Each node applies an activation function to introduce nonlinearity. Common choices are 1 sigmoid function, used in probability and logistic regression. F, Z, equals 11 plus EZF, Z, equals \frac 1 1 plus E caret ZF, Z, equals 1 plus EZ1. Converts output into a probability range, 0 to 1. Used in classification problems. 2 ReLU, rectified linear unit, used in deep learning. F, Z, equals max, 0 Z, F, Z, equals \max, 0, Z, F, Z, equals max, 0 Z. Efficient in handling vanishing gradients. Used in CNNs, DNNs, and deep architectures. 3 tan function, used in recurrent neural networks. F, Z, equals EZ plus EZF, Z, equals \frac E caret Z, E caret Z E caret Z plus E caret ZF, Z, equals EZ plus EZ. Normalizes output between -1 and 1. 4 softmax function, used in multi-class classification. F, Zi, equals EZI sigma j equals 1 nes jv, Z underscore I, equals \frac E caret Z underscore I \sum underscore j equals 1 caret n E caret Z underscore jf, Zi, equals sigma j equals 1 nes jz. Converts output into probabilities that sum to 1. 3 backpropagation, gradient descent for learning. Neural networks learn using backpropagation, which minimizes the error using gradient descent. 1 loss function, error calculation. If it's a regression problem, continuous output, use mean squared error, MSE. L equals 1 n sigma I equals 1 n, y caret, 2 L equals \frac 1 n \sum underscore I equals 1 caret n, y underscore I, \hat y underscore I, caret 2 L equals n1 I equals 1 sigma n, y caret, 2. If it's a classification problem, use cross entropy loss. L equals sigma I equals 1 nulig, y caret, L equals \sum underscore I equals 1 caret n y underscore I \log, \hat y underscore I, L equals I equals 1 sigma nulig, y caret. 2 gradient descent update rule, weights adjustment. W equals W8 L W equals W, \eta \frac partial L partial W equals W8 WLB equals B8 LBB equals B, eta \frac partial L partial BB equals B eta BL. Where eta eta equals learning rate. LW \frac partial L partial WWL equals partial derivative of loss function W.R.T weights. 4 mathematics branches involved. 1 linear algebra. Matrix operations for weight updates. Representing multiple inputs as vectors. 2 calculus, differentiation. Used in gradient descent for optimization. Backpropagation relies on partial derivatives. 3 probability and statistics. Used in output layers for classification, example softmax, cross-entropy loss. Bayesian learning methods. For optimization theory. Used for finding the best weights and biases, example atom optimizer. Summary. Each node follows the formula z equals sigma yxc plus b z equals / sum w underscore I x underscore I plus b z equals sigma yxc plus b a equals f, z, a equals f, z, a equals f, z. Activation functions introduce nonlinearity, ReLU, sigmoid, 10. Backpropagation and gradient descent optimize weights. Math branches, linear algebra, calculus, probability, and optimization. The power of deep neural networks, DNNs. 1. Understanding DNNs, the brain behind AI. A deep neural network, DNN, is an advanced form of artificial neural networks, ANNs, that consists of multiple hidden layers. These networks are capable of automatically learning complex patterns, making predictions, and improving decision-making across various fields. 2. Why are DNNs so powerful? DNNs mimic the human brain, allowing machines to learn automatically from raw data, identify hidden patterns, perform complex decision-making, generalize to new, unseen data. Key advantages of deep neural networks. 1. Feature extraction and learning, no manual effort. Unlike traditional machine learning, where engineers manually define features, DNNs automatically learn the best features from raw data. Example. Face recognition, DNNs detect edges, eyes, and facial features without manual programming. 2. Handling large and complex data. DNNs can process massive datasets and handle unstructured data, example images, text, audio, better than traditional ML models. Example. Google Translate uses a transformer-based DNN to translate languages in real time. 3. Deep learning for pattern recognition. DNNs are exceptional at recognizing nonlinear relationships in data that traditional models fail to capture. Example. Healthcare diagnosis, DNNs detect cancer from medical images better than human doctors in some cases. 4. Self-improvement and adaptability. DNNs continuously learn and improve as they process more data, enhancing prediction accuracy over time. Example. Tesla's autopilot AI improves driving decisions as it collects more driving data. 5. Universal approximation power. Mathematically, a DNN with enough neurons can approximate any function, making it useful in finance, robotics, speech recognition, and more. Applications of deep neural networks. Business and finance. Heavy checkmark stock market prediction chart increasing. Heavy checkmark fraud detection. Heavy checkmark customer behavior analysis. Healthcare. Heavy checkmark disease prediction. Heavy checkmark medical image analysis. Heavy checkmark drug discovery. Autonomous vehicles. Heavy checkmark self-driving car vision. Heavy checkmark real-time traffic analysis. Manufacturing and engineering. Heavy checkmark predictive maintenance. Heavy checkmark defect detection. Brain AI assistants and chatbots. Heavy checkmark voice recognition, Alexa, Siri, studio microphone. Heavy checkmark AI-powered customer support. Future of DNNs. With advancements like quantum AI, explainable AI, XAI, and neural architecture search, NAS, DNNs will become even more powerful, driving the next wave of artificial general intelligence, AGI. From a deep neural network, DNN, perspective, decision-making at different levels within an organization can be understood as follows. Pradeep K. Suri, author, researcher, and AI/ML architect. 1. Top management level, decision support system, DSS. Function, strategic decision-making based on high-level data insights. DNN role, the final output layer of the neural network represents high-level aggregated insights. These outputs are derived from complex transformations applied to raw data. Interpretation, the DSS leverages probability-based results, sigma w underscore ix underscore I plus b, to generate strategic reports for top management, ensuring informed business decisions. 2 Middle management level. Function, tactical decision-making, bridging operational and strategic levels. DNN role, the middle hidden layers represent feature extraction, transforming raw data into meaningful patterns. Interpretation, neural layers perform weighted computations, sigma w underscore I x underscore I plus b, to provide insights for mid-level reports, helping managers optimize processes. 3 Operational level, data science and AI applications. Function, day-to-day operational decision-making using real-time data. DNN role, the first few hidden layers perform fundamental computations using linear algebra, probability, and calculus to process raw data. Interpretation, at the operational level, neural network nodes help in forecasting demand, optimizing supply chains, and monitoring transactions. DNN-based decision-making in real-world applications. Deep neural networks, DNNs, play a critical role in decision-making at different organizational levels. Let's break down their applications with examples for top management, DSS, middle management, and operational level. 1 Top management level, DSS, decision support system. Strategic decision-making. Focus, long-term business strategy, risk assessment, and high-level analytics. DNN role, the final layers in the network aggregate insights from previous layers, providing predictive analytics and strategic reports. Example. Stock price forecasting, a DNN analyzes historical stock data, economic indicators, and market sentiment to predict future stock trends. Customer retention strategy, a DNN clusters customers based on purchase behavior and suggests personalized retention strategies. How DNN helps? Uses time series forecasting to predict sales trends. Detects early warning signs of financial risk. Suggests optimal pricing strategies for profitability. 2 Middle management level. Tactical decision-making. Focus, improving operational efficiency and monitoring performance. DNN role, intermediate layers extract patterns from data to optimize processes. Example. Supply chain optimization, a DNN predicts demand for raw materials based on historical sales data, reducing excess inventory costs. Employee performance analysis, a DNN evaluates employee KPIs using HR analytics and recommends promotions or training. How DNN helps? Identify bottlenecks in production. Optimizes budget allocation for marketing. Improves customer segmentation for targeted advertising. 3 Operational level, AI and data science applications. Day-to-day decision-making. Focus, automating processes, real-time monitoring, and minimizing errors. DNN role, the initial layers handle raw data, extracting low-level features. Example. Fraud detection in banking, a DNN identifies anomalies in transactions to flag suspicious activities in real time. Predictive maintenance in manufacturing, sensors in machines feed data to a DNN, predicting failures before breakdowns occur. How DNN helps? Classify defective products in real time. Automate loan approvals based on credit scoring. Detects cybersecurity threats using pattern recognition. Bridging the gaps between these levels. Top management, DSS, needs aggregated insights. Rightward arrow uses final DNN layers. Middle management refines business processes. Rightward arrow uses intermediate DNN layers. Operational level executes real-time decisions. Rightward arrow uses raw data in initial DNN layers. Conclusion. A deep neural network, DNN, acts like a human brain for businesses, heavy checkmark extracting patterns, feature learning. Heavy checkmark processing high-volume data, big data analysis, bar chart. Heavy checkmark providing actionable insights for decision-making. Would you like a custom Python example showing how DNNs analyze data for real-time business insights? Thank you.